Hello and welcome. In this video, we're going to look at how to solve for a series circuit. The first prompt here asks us to solve for the total resistance that is called RT. Right? And in series, RT is the sum of all of our series resistances. So we'll say that it's R1 plus R2 plus R3. We'll just sum up all of our resistors. And when we look at these resistors, we see that each one has a kiloohms at the end of it. So we need to make sure that we account for that in our total resistance final answer here. When we tuck this into our calculator, we can say that it's actually 10 kiloohms plus 32 kiloohms plus 88 kiloohms, and that gives us 130 kiloohms, right? It doesn't say 130 kiloohms because I didn't put the kiloohms in there, but I did remember it, right? So 130, and then I can just add whatever the ending was for every one of these resistors at the back here. That works really well when all of the resistors are in the same notation, right? They're all in kiloohms. But if one of them's in mega ohms, you got to make sure you remember to count for those zeros that mega ohms represents. Okay, so now that we have our total resistance, we can use that to find our total current, IT. And this requires the use of Ohm's law. So we'll bring out our Ohm's law triangle. That is voltage on top, current, and resistance. And with this, we can solve for the equation we want to use. We know we're looking for IT, so we'll circle I. That's going to give us voltage over resistance. So our current is equal to voltage divided by resistance. Specifically, since we're looking for the total current, we'll need the total voltage and the total resistance. We have the total voltage. Since there's only one voltage source in the circuit, we know that that has to be the total voltage. We just found the total resistance because we just calculated it up here, right? So 130,000. So we can just plug that in. We can say that our current, IT, is equal to our voltage source of 28 volts divided by our total resistance of 130,000 ohms. We'll plug that in. Say that we have 28 on bottom or on top, and we'll divide that by 130. Remember this 1,000. This is where it really matters because this 130 is not the same answer output, right? It gives us 0.215, and that's not small enough. So if we put in the full 1,000, though, another 3 zeros after the 130, then we get to our actual current, right? It's a really small current because we got a lot of resistance in this circuit. So that means our answer is 2.15 times 10 to the negative fourth. Problem is that negative 4 here is not in engineering notation, so we need to make sure that that fits into engineering notation, which means it can't be negative 4. It can be negative 3, it can be negative 6, negative 9, negative 12, any of those, but it can't be a multiple that isn't of 3. And so we need to move this. And right now, this negative 4 is representing the fact that this decimal point here is at the negative 4 locations back from 0. So we're going to move it forward 1 so that it's at its negative 3 spots back from 0. And that's going to give us our milli location. We'll call that as a tiny m. And so we'll say that our IT, our total current, is actually equal to 0.215 milliamps, MA. Okay, so now we're on to our total power. Our power equation is using the power law, and they say total power dissipated in all resistors, so we're looking for PT. Now we need to pull out our power law. Our power law is the same as our Ohm's law as far as the triangle goes. Our triangle comes out and it has power on top, current and voltage on bottom here. And we can solve for the equation we want to use in here. We can say that if we want to know power, then we can use voltage times current, and that's going to get us the power output. We'll write that. We'll say power is equal to current times voltage. Specifically, we're looking for total power, so we need to use our total current and our total voltage. We'll plug that in. Say that PT is equal to our current that we have up here, 0.215, and that's in milliamps, multiplied by our voltage source total, and that's this 28 volts over here. 28. Plug that into our calculator here. This is going to be a wattage, and wattages are usually dependent on both the voltage and the current, and a lot of times our current is pretty darn small. So this is actually going to probably end up being in a milliamps value. So we can account for all the zeros in our current right now and say that we have 0.000125, right? That's in amps. That's the same exact thing as this 0.215 milliamps, right? We just moved it completely out of notation all the way back down to base. And then we can multiply that by 28. Right, that's going to give us that really small number, and we can move that decimal over too. We can say that our power isn't actually 0.00602 watts, right? We can move that over and plug it into engineering notation by dropping it back 1, 2, 3 locations to the -3 spot. So it's actually 6.02 milliwatts. That's great. And in fact, it's so nice that we can even leave off these zeros and know that whatever we multiply this milliamps by, this voltage over here, it's going to end up giving us a milliwatt output over here. And so we end up with 6.02. So there is some level of shorthand that you can use with these notation values. Just be careful. And if you are uncertain if you've got it correctly, pull it all the way back down to 0 and account for every one of the zeros that you know you have. Okay, let me know if you guys have any questions.